When I was in my junior year of undergrad, I took a course called Real Analysis. And at the beginning of the term, the professor walked into the room, sat down, heaved a heavy sigh, and said to us, "You're math majors. You're not allowed to forget anything." That's one of the truest statements a human has ever said to me. And I feel that no course exemplifies that statement more than differential equations. Differential equations is in many ways a capstone math course, and I see it almost as a celebration of all the math that you have ever learned. The goal for today is to very briefly review some of the most essential topics from algebra and pre-calculus that I think are the most likely to have been forgotten in the years since you took those classes. Of course, you're also going to need to know material from Calculus 1, 2, 3, and 4 in this class. But because you took those courses more recently, it's more likely that you are going to remember how to do things like take derivatives and integrals. The first topic that I would like to review is exponentials and logarithms and some of their properties and how we solve equations containing exponentials and logarithms. And I will be focusing on the natural exponential and on the natural logarithm because these two functions show up so much more often than the other kinds of logs and exponentials. We have our exponent properties. For example, if you have a product of exponentials, then that can be turned into a single exponential where the two exponents have been added together. If you have a quotient of exponentials, that corresponds to a subtraction of the exponents. If you have one exponential raised to a power a, and then you raise that entire expression to the power c, then that's equivalent to the power of the two exponentials. And if you raise e to the power natural log of something, then the e and the natural log cancel out, and you're left just with the something that was inside natural log. So let's try and use these principles to simplify the expression e to the power 2 natural log of x plus 3. Now if you want to use this property, e to the natural log of a, you need to make sure that natural log of something is the only thing in the exponent of e. Until natural log is completely by itself in the exponent of e, you are not yet able to cancel the e and the natural log out. So in my expression, e to the power 2 times natural log of x plus 3, I'm going to need to get rid of the plus 3, and I'm going to get rid of the multiplied 2, so that natural log of x is alone in the exponent of e. To that end, I'm going to use some of these exponent properties listed. For example, the first property suggests that if I have something that is added in the exponent level, then I can turn that into a product at the base level. And I can split this expression up as e to the 2 times natural log of x multiplied separately by e to the 3rd power. Now I'm still working on getting natural log of x by itself in the exponent level, so I need to get rid of that multiplied 2. And to that end, I'm going to use the third property in this list, which tells me what to do if I have a product in the exponent level. It says that I can rewrite this as e to the natural log of x, quantity raised to the power 2, and then we have that times e to the 3rd power from the previous line. Finally, I have e to the power natural log of something, nothing else in the exponent level. So the e and the natural log cancel, and I'm left with x to the power 2 multiplied by e to the 3rd power. Or in more standard notation, e to the 3rd power times x squared. This would be the simplification of the expression that we were given in this exercise. Likewise, the logarithms have their four properties. A product inside a logarithm becomes a sum outside of the logarithm, a quotient becomes a difference, exponents become constant multiples, and natural log of e to the something is equivalent to just that something. So let's use some of those principles to help us to solve some equations that contain logarithms. We're going to start with a simple example and then move on to more complicated examples that are more similar to what we'll encounter during our work in this class. So we want to solve natural log of y equals x plus 3, and in particular we want to isolate y, which means that I need to get rid of the natural log that is currently encasing y. So I'm going to apply the exponential to both sides of the equation. Now when I do this, I have to be careful to make sure that I apply the exponential to the entire left side and the entire right side of this equation. What I cannot do is apply the exponential one term at a time and take e to the x separately from e to the third power. That is not going to be equivalent to the equation that you started with. So now on the far left side, I have e to the power natural log of something and nothing else in the exponent. So the e and the natural log cancel out, and I'm left with y is equal to e raised to the quantity x plus 3. This is the given equation solved for y. The situation becomes more complicated when we have more than one natural log in the equation. Natural log of y plus 1 take away natural log of y minus 1, for example. Let's try and solve this for y. So the first thing that you want to do when you have multiple natural logs is you want to try and combine them into a single natural log. That way you can cancel out that combined logarithm using an exponential. To that end, I'm going to use the log property that says that if you subtract on the outside of a natural log, that's equivalent to dividing on the inside of a natural log. Now that I have a single natural logarithm, I can destroy that natural logarithm by applying an exponentiation with base e to both sides. So e to the natural log of y plus 1 over y minus 1 is equal to e to the power x. The e and the natural log cancel, and I'm left with y plus 1 over y minus 1 equals e to the x. Now my goal is to solve this equation for y. So I'm going to begin by clearing the fractions, multiplying both sides by y minus 1 so that I get e to the x times y minus e to the x times 1 on the right side. And now, in pursuit of solving for y, I'm going to gather all the terms that contain y to one side of the equation and all of the terms that don't contain y to the other side. So by doing this, I get y minus e to the x times y is equal to negative e to the x minus 1. Now the advantage of gathering all the terms that contain y to one side of the equation is that you can now factor y out of the expression on the left side. So solving for y by dividing by 1 minus e to the x, I get negative e to the x minus 1 over 1 minus e to the x. This would be the solution of the equation that was given to us. We can also use the properties of exponentials and logarithms to solve equations containing exponentials. Here we have the equation 3 e to the 2t plus 1 equals 17. So let's try and solve this for t. The first thing that I'm going to do is I'm going to isolate the exponential. So I'm going to get rid of the 1, and I'm going to get rid of the 3. Now that the natural log has been isolated, it's vulnerable to attack by its arch nemesis, the natural log. Now when I apply the natural log to both sides, then the left-hand side, the natural log and the natural exponential cancel, and I'm left with just 2t is equal to the natural log of 16 over 3. So t is equal to the number 1/2 the natural log of 16 over 3. This would be the exact solution to the given equation. The second thing that I would like to review is how to solve systems of equations, both systems of linear equations and systems of exponential equations. For an example, let's consider the system of linear equations given below, 2x plus 3y equals 7 and x plus y equals 16. When you're solving a system of linear equations, there are typically two standard methods. And the first one is called method of substitution. In method of substitution, you take one of the equations in your system and isolate one of the variables. For example, you can take equation number 2 and subtract x from both sides in order to isolate y. Then you can plug this back into equation number 1, giving you 2x plus 3 times 16 minus x is equal to 7. So this will give us 2x plus 48 minus 3x is equal to 7. And therefore negative x is equal to 7, take away 48. So x is equal to positive 41. If I plug that back into the first equation, the one which relates x and y by y is equal to 16 minus x, if I plug 41 into x's position, then I get y is equal to 16 minus 41, which is equal to negative 25. So these two numbers, x equals 41 and y equals negative 25, will make both of the equations in the system true at the same time. And therefore that pair of numbers would represent a solution to the system. The second method that can be used to solve a system of linear equations is the method called method of elimination. If you've taken linear algebra, this is the algebraic method which is closest to the method of row reduction that you learned in linear algebra when working with matrix representations of systems. In method of elimination, your goal is to manipulate this system of equations to get two opposite terms, which would cancel out if you added the terms together. There are a couple of different ways to accomplish this, but the one that occurs to me first is to multiply the entire second equation by minus 2. If we did this, we get 2x plus 3y equals 7, negative 2x minus 2y equals negative 32. And if we then add those two equations together, the opposite terms formed by 2x and negative 2x cancel out. The y's sum together to give us just a single positive y, and the 7 and the negative 32 become negative 25. Once you know what y is, you can use either one of the equations to find the value of x. So by this secondary method, it is also possible to obtain the solution x equals 41 and y is equal to negative 25. It's also possible to solve a system of equations where the two equations are of exponential format instead of linear. For example, we have a system where we require that b e to the 2k is equal to 2 and b e to the 5k is equal to 10. So what would the values of b and k have to be in order to make both of these equations true? When we're faced with a system of exponential equations of this format, our traditional technique is to start by dividing the two equations. And it seems easiest to me if I take the second equation and divide it by the first. So on the right side, I have 10 divided by 2, and on the left side, I have the b e to the 5k divided by b e to the 2k. Now, by virtue of doing this, we have obtained an equation which can be simplified pretty dramatically. The two b's completely cancel out, and the two exponentials can be combined using the exponent properties. So e to the 5k minus 2k is equal to e to the 3k, and that needs to be the same thing as 5. So now I can solve this exponential equation for k, and I'm going to start by applying the natural log to both sides. So 3k is equal to the natural log of 5, and therefore k itself is equal to 1/3 natural log of 5. Now the only thing left for me to do is to try and figure out the value of b. To that end, I can use either one of the two equations in the system. I might choose the first equation basically at random. So if I plug in the known value of k, I can reduce this to be e to the 2/3 natural log of 5. Now I can simplify this exponential, but before I do, I need to make sure that the natural log of 5 is the only exponent on the exponential. So I'm going to move that 2/3 to the side. Now that I have isolated natural log of 5 in the exponent level, e and natural log cancel, and I'm left with b times 5 to the power 2/3 is equal to 2, and therefore b is equal to 2 divided by 5 to the 2/3. So this value of k, 1/3 natural log of 5, and this value of b, 2 divided by 5 to the power 2/3, together form the solution to the system of exponential equations that I was given. The last topic from algebra that I would like to review is the topic of partial fraction decomposition. You probably learned this in Calculus 2 when you were using this to calculate integrals of rational functions. We're going to need it again in this course, in particular toward the end of the class when we study the Laplace transform in Chapter 7. And we're going to consider 3 different cases. In the first case, we're going to consider what we should do when we're decomposing something whose denominator has distinct linear factors. For example, here we have the factor x minus 3 and x plus 1, both of which are linear, and neither of which is repeated. They are both different factors from one another. In this specific case, where all the factors in the denominator of the expression that you're trying to decompose are distinct and linear, you can use a special shortcut method called the Heaviside cover-up method. Heaviside cover-up method says, I want to split this fraction into 2 simpler fractions, one of which has a denominator of x minus 3, and one of which has a denominator of x plus 1. Now, what number should I put in the numerator of each fraction in order to make the decomposed side equal to the original fraction? In the Heaviside cover-up method, you can ask yourself what value of x would cause this denominator to zero out. The value of x that would cause that denominator to zero out is equal to x equals 3. So I'm going to go over to the left side of the equation, the heavy side of the equation, and cover up the factor x minus 3 that I'm working on right now. And I'm going to plug x equals positive 3 into the expression that remains. 1 over x plus 1 becomes 1 over 3 plus 1. That number, 1/4, is the coefficient on the top of this fraction. Likewise, for the second fraction, the denominator zeroes out when x is equal to minus 1. So going over to the left side, the heavy side, we'll cover up the x plus 1 factor and plug x equals minus 1 into what remains. So having done that, we get the number negative 1/4, and that's the coefficient on the second fraction. That's Heaviside cover-up method. It can only be used when you're decomposing a rational function where the denominator contains linear factors with no repeated factors. In another case, your denominator might have factors which are quadratic and which cannot be factored any further unless you stray into the territory of complex numbers. For example, here, we're trying to decompose 1 over x squared plus 2 times x squared plus 1. And neither x squared plus 2 nor x squared plus 1 can be factored any further. So we would call them irreducible. So we would still like to break this fraction down into a sum of two simpler fractions, whose denominators are the irreducible factors x squared plus 2 and x squared plus 1. But this time, we cannot expect the numerators to be just numbers. If the denominator is of degree 2, then we need to expect the numerator to be of degree 1, a degree which is 1 smaller than what you have at the bottom. So I'm going to guess that the numerator has the form of a generic linear expression, ax plus b. And over here, another linear expression, let me call it cx plus d. Now I'm going to multiply through by the least common denominator in order to clear the fractions. And I'm going to try and do some work to determine the values of a, b, c, and d that would be needed to make this equation a true statement. On the left-hand side, I have 1, and on the right-hand side, I have the quantity ax plus b times the quantity x squared plus 1 plus the quantity cx plus d times the quantity x squared plus 2. And if I multiply that out, I get ax cubed plus bx squared plus ax plus b plus cx cubed plus dx squared plus 2cx plus 2 times d. Now I'm going to go into the equation and I'm going to analyze which terms contain an x cubed, which terms contain an x squared, which contain an x, and which are constant. Now on the right-hand side of the equation, I have two terms that contain x cubes. I have an ax cubed and I have a cx cubed. But on the left-hand side of the equation, I don't have any x cubes. So I'm going to set ax cubed plus cx cubed equal to 0. And this in turn implies that a plus c itself, the constants, the coefficients of x cubed, must sum together to equal 0. Those terms must cancel out in order for there to be no x cubes on the left side of the equation. Likewise, for the x squared terms, I have a bx squared and a dx squared, but I have no x squareds on the left side. So b plus d must be equal to 0. If I look at the x terms, I have ax and 2cx, so a plus 2c must be also equal to 0 because I have no x's on the far left side. And if I look at the constants, the constant b and the constant 2 times d must be equivalent to the constant 1 on the far left side of the equation. So this gives me a system with 4 equations and 4 unknowns, which can be solved for the values of a, b, d, and c. For example, equation number 1 implies that a and c are opposites. And if I plug that into equation number 2, I get negative c plus 2c equals 0, which means that c is equal to 0, which means that a must also be 0. If I look at equation number 2, equation 2 implies that b and d are opposites. If I plug that into equation number 4, then that gives me that negative d plus 2 times d is equal to 1, which implies that d itself is equal to 1. And therefore, b must be equal to negative 1. So if I put those values back into the format that I set up for the partial fraction decomposition, ax is going to become 0x and is going to vanish. B is going to become negative 1. Cx is going to become 0 and will just vanish. And the d is going to become positive 1. This expression would be the decomposition of the rational expression that we were given at the start of the problem. Finally, let's consider the case of repeated linear factors. Here, I am looking to see if I can decompose the expression 2x plus 1 over x minus 4 quantity squared. So this denominator contains the linear factor x minus 4, which has been repeated to a total of 2 times. In this case, you can break this down as a sum of 2 different terms, x minus 4 and x minus 4 squared. But the nice thing is that because the factor is basically linear, basically degree 1, it's just been repeated, you can put an expression of degree 0 of one smaller degree in the numerator, so you can guess that the numerator is just a constant. Now once again, because I do not have the case of distinct linear factors, because one of the factors was repeated, I can't use Heaviside cover-up method, that shortcut. But I can clear the fractions. And when I do that, when I multiply through by the least common denominator to clear the fractions out, I get 2x plus 1 is equal to a times x minus 4 plus b. Now if I look at the x terms, then I get 2 x's on the left and ax is on the right. And if I look at the constant terms, I get 1 for the constants on the left and negative 4a plus b for the constants on the right. So immediately I know that a must be equal to 2. And if I plug that into the second equation, I find out that b must be equal to 9. And therefore I can split up the expression that I was given as a sum of 2 simpler expressions. 2 divided by x minus 4 plus 9 divided by x minus 4 quantity squared. This concludes our review going forward into differential equations. Every single one of the exercises done in this video represents something that we are going to have to do during our work in the course. In addition to all of this stuff, you're going to need to know how to take derivatives and integrals, including partial derivatives and partial integrals.